McKinsey. Why does McKinsey exist? Boston Consulting. These are big organizations. All of them should be replaced by, people say AGI is 2 years. And people who actually work in these labs and frontier labs, I know a lot of them, they're basically saying just like, we're not going to have AGI in 2 years. A lot of people were basically saying, my God, OpenAI has figured out a new architecture. They figured out like AGI. That's absolutely not true. The architectures are the same. The CEO of this company is Zhilin Yang. He's my former student at CMU. He is one of the smartest people I know. China has strong talent. They now have the resources. So I think they'll be able to compete with the US. So if I am a CEO of a company and I have a better view of the future than my competitor, I'm going to win.
So you think that all the LLMs are basically commodities?
I think they're going to be commodities.
Yeah.
There's only one example, which is Roomba. There's no other example right now where a robot is useful.
In 2005, neural networks were a joke, third choice behind support vector machines. At the time, Russ Salakhutdinov was working in finance, but by a chance encounter, he bumps into Geoff Hinton on the street in Toronto. Hinton drags him into his office, and he walks out doing a PhD in deep learning before deep learning was even a term. And if you're not familiar with Geoff Hinton, he's widely considered the godfather of AI. So he was in the middle of it all. 20 years later, Russ has done basically everything. He sold his startup to Apple. He worked on their secret self-driving car project Titan. He became a professor at Carnegie Mellon, and he just left Meta Superintelligence Lab to start Sooth Labs, which just raised $50 million to build AI that forecasts the future. This episode, Russ tells me that the frontier labs are all building commodities, how the people actually building AGI don't think that it's 2 years away. He explains why Cursor and half the startups you know are actually running on Chinese open source models, how Yang Zhilin, the CEO of Kimi, was one of his smartest PhD students, why the only useful robot in the world is still the Roomba, and why AI should replace McKinsey, Bain, and BCG. Let's get into it. So you've been at the center of modern AI since, basically the beginning. So I want to walk through that journey a little bit before we get into some of the stuff that you're working on now. So first of all, why did you decide to do a PhD in machine learning in the mid 2000s? Where did you see things headed?
It's a very good question. So my story is kind of a little bit unusual because I was very interested in AI. So I started my master's degree at the University of Toronto in early 2000s. I did my master's and then I kind of left and went into banking. So I was in financial sector for a year, and it's almost like by luck, I started doing my PhD. At the time I was working with Geoff Hinton. He was, working with me when I was doing my master's, and I didn't know whether I wanted to do PhD or not. But then at one point I was walking down the street and I bumped into Geoff Hinton, and he basically said, I have this amazing idea, these models, these deep learning models, you can learn multiple layers of representation and everything. And so he essentially dragged me to his office and started showing to me what he's been working on. And I think that was so inspirational to me that I was basically saying, can I come and do a PhD with you on this topic? And he sort of, he made it happen. He's like, okay, why don't you apply for your PhD program and everything? Come and work with me. And so, I started my PhD in 2005, 2006. And at that time, I think deep learning has been sort of, it just was very early, wasn't very clear what it's going to work. These neural networks, they were very sort of looked down upon because at the time, people were looking at statistical machine learning sort of theory and, something that's more rigorous. And neural networks have always been looked at as these are nonlinear systems that people just optimizing without really understanding what's going on, right? And so, but that's when some of the early deep learning models were trained, and I, did my PhD, and then with Geoff, and then moved to MIT to do my postdoc and such. So, and then the rest is the history, basically.
Yeah. But why were neural nets so exciting to you? What was he articulating to you that made it seem so interesting?
Yeah. Geoff has a very good. I think he was just his excitement, and it convinced me that this is going to be an interesting PhD to do, interesting topic to do my PhD in.
Yeah.
I think it was part of it, right? Because I think that at the time, people were, again, neural networks have at that time, neural networks been looked down upon as these sort of systems. They've been around for 20 years. They never worked. They're number third choice of any sort of method at the time. Methods like support vector machines and more rigorously, more mathematical rigor behind those models. But Geoff was one of the first people who showed that learning these stacked systems, learning these deep systems, right, can actually give you, so you had a mathematical justification for us, which is a beautiful math behind showing that, these models can improve something. It's called variation low bound. And I think it was exciting that I could see that this could have a strong potential in the future.
And what were the use cases that he was excited about, or that you were excited about? Or was it more just, the math was beautiful?
No. Yeah. So the math was beautiful. That's number one, because for the first time you could actually say, okay, there is mathematical rigor behind these models. It's not before that people were sort of, training neural nets. It was always a little bit there is some optimization, you do optimization, but there's no like understanding, there is no sort of connection to statistical machine learning. I mean, there were some, but not as rigorous, right? And it was always like this field had always been looked down upon. I mean, you'd probably ask Jan LeCun. Jan LeCun was like working on these models for a long time, but he could never get the recognition in early days for any of his work because it was just kind of like didn't work, right? Because the scale was small and one of the interesting things that showed up early on is a glimpse into generative models. So at the time we were generating images of handwritten digits, these MNIST
This was
digits,
in the mid 2000s?
It's the mid 2000s, yes.
Wow.
And it was one of the early days that you could show that these deep models, something is called deep belief network, and then we were working on deep Boltzmann machines, were initially the models that can sort of like generate, these nice looking handwritten digits, like MNIST digits, right? And it showed that, hey, these models are capable of going beyond multiple levels. They can learn multiple levels of representation. And that basically excited a lot of people, both the math behind it, plus that they showed the promise. And they were sufficiently different from anything else that people were working in the community. And sort of like, and at a time in 2005, 2010, it was like a small group of people who were essentially working on these models, making progress on these models.
And when did you finish your PhD?
Finished my PhD in 2009.
Okay, and then you went to MIT to do your
And then I went
postdoc.
to do my postdoc. Yeah, so I was doing my postdoc with Josh Tenenbaum, fantastic professor and fantastic colleague of mine. Josh was sort of looking at deep learning models, but he was also looking on these sort of non-parametric Bayesian models. These are sort of classes of models. I mean, Josh is a cognitive neuroscientist, cognitive scientist, and so it was great hanging out at MIT. MIT also had a lot of strong computer vision people and such, so it was a good experience. And then I came back to Toronto as a faculty.
Yeah. So it seems like, yeah, you were very excited about like the generating digits. Like that was very interesting. But then it seems like when AlexNet came out that everyone's focus basically shifted to classifying images rather than generating them.
So what's happened early on is that if you take, like at the time we didn't have GPUs, if you sort of train these multi-layer neural networks on something like MNIST, there's a class of datasets like, these old toyish datasets, CFAR, you could never beat sort of competing methods like support vector machines. And these generative models showed the promise that if you actually learn these generative models and then convert them into discriminative models like classification systems, they would actually work much better. So this notion is that, learning how to generate images basically gives us the representations that we need to actually do classification. And then after ImageNet competition, after AlexNet, people sort of realized, well, convolutional neural networks actually do work. And they work remarkably well. And after AlexNet, people actually shifted to these discriminative models because that was, they've solved, I think AlexNet solved one of the key vision problems, right? Which was it was ImageNet competition. And it was a million images, very diverse images. And people were looking at it over the past, 2 to 3 years, like gigantic labs at Berkeley, Oxford, MIT. They had lots of, PhDs and computer vision people were participating. And I think AlexNet was the first model that showed that you can improve performance by like 50%. So you can imagine Alex Krzyzewski, Ilya Sutskever, and Geoff Hinton, 3 people. They've built, fairly simple ConvNet, but they scaled it, and they were the first ones to scale it on GPUs. And they've shown that this model was able to improve over whatever people have done by 50%. And they've able to do it to the point where there was a lot of skepticism initially, like people couldn't believe it. Like it's remarkable, right? When you see the result, you say, that cannot be true. It's too good to be true. So it took people like a couple of months to actually verify and say, okay, this is real.
Yeah. So you were there when AlexNet came out.
I was there when AlexNet came out. That's right. I came from my postdoc back to Toronto, and yeah, it was.
Were you skeptical?
No, I wasn't skeptical of the results. I knew like Geoff was kind of like on it, so it's one of the things that Alex Krzyzewski has done very well is he optimized some of the computations on early versions of GPUs, which required like a very strong engineering talent to do it. Because scale, that was one of the earlier kind of like points where the scale actually showed big success.
Interesting.
So
And then,
that was the turning point
sorry.
for computer vision. That was the turning point for computer vision researchers. Like from that point on, Google, all the other major labs and academics started basically converting to deep learning.
So what were you focused on before, like what was your research focused on before AlexNet came? And then did your research shift when it came out and you got really excited by it?
So my research was kind of like, I've never looked at, I mean, I was looking at vision and generative models. I think my research, I wasn't part of the AlexNet because it was like a fairly strong engineering effort. My research kind of like started shifting after AlexNet because one of the things that my lab's been looking at Toronto also is early versions of caption generation. So once we started seeing that these models are actually pretty good, then we've started looking at models that, given images, generate descriptions for those images. This was one of the early, I remember talking to some of the computer vision folks, and then at the time, classification detection was the thing to do. But a lot of computer vision people were saying that, well, I want a system where I show you the image. And I just don't want to say, well, there's a car in this image over here, and then there is like, a person standing here. I actually want the system to describe me the scene. I want the system to look at it just like human, tell me like, oh, that's, it's a sunset. You have a beautiful beach here. You have people walking on the beach, and sort of like, just tell me what's like, that's the, a way of much better understanding than if me running a classifier says, is there a person there or not? Yes or no. Is there a car there? Yes or no, right? Which is what the field was. And so like early on, these recurrent neural networks coupled with vision systems started showing progress. And this is what, we were looking at.
I had never even thought about that as a thing until like LLMs came out.
No, at the time, people were kind of like, and this was one of the early sort of models that showed promise. And then early on, people started looking at attention mechanisms. So we had a paper called Generating Image with Visual Attention. So the model would attend to different objects when it describes different parts of the scene. So this was like earlier versions. I mean, they never worked very well because it all was like very small scale, right? And then in parallel, my lab was also looking at image generation, early version of image generation. And we had one of the papers, one of the students, Nitish Srivastava, was working with another student on sort of these models that could generate small images, small patches of images. I give you the description. So it's like reverse. Give an image, you generate the caption. But then we started asking, well, if I give you the caption and I tell you what it is, can you generate me image? And there was a fun story. We had a paper that was one of the early papers that would generate those images, and wasn't very good model. Again, like the scale was pretty small. We didn't use GPUs. But we started seeing early versions of, like, for example, I can tell you a plane is flying in rainy skies. And we try to sort of generate something that looks like a plane in kind of like darkish background. And then we would say a plane is flying in not in the rainy sky, but in blue sky. And the image would change completely, like same plane, but the background would be different. So it was one of the early systems with like, if you look at distribution of pixels in one image versus another image, it's very different. So the model would be able to generate something very different, even though the caption was exactly the same, except for rainy, you would change rainy skies to blue skies, right? So one word would change, would impact the entire distribution of what the model was able to generate. And then at that time, we started thinking kind of like, well, can we actually generate images that don't exist in the real world? Because we wanted to test the ability of these models to generalize. So you can kind of like say, well, a school bus is parked in the street, or we can say a school bus is flying in the sky. So can the model generate the school bus? Can the model generate the sky and kind of like make it look like it's flying in the sky, right? And so it was early versions of these systems. And, there's arguments is, does the system understand what it's doing or does it not understand what it's doing? And then, Geoff Hinton was early kind of like promoter by basically saying, look, if I generate, a cat sitting on the beach drinking beer and the model can actually do it, does it mean that it understands what it's generating or not, right? So there's arguments because those things don't exist in the real world, right? But if the model can generate and kind of hallucinate and such, it means that it has an understanding. And we had this one, the student, Elman Mansimov. I think he then, was a PhD student at NYU, but he had like a cool idea of basically he generated the image of a toilet sits open in the grass field, right? So a toilet sit in the grass field, like in the open grass field, and it would sort of generate like a grass, like you can see like green, and again these models were very primitive, and would generate like a white, kind of like looks like a toilet. We just did it for fun, right? And I was giving a talk, and then somebody noticed that like actually, if you ask Google Images, give me a toilet sit in the green grass, there was actually somebody took a picture, and if you Google search, like one of the top pictures is the picture of like somebody put like a toilet seat in the grass field, right? And people were saying, well, but is your model really can generate, because it already exists there, right? I mean, Google can do better than your model can. But what was funny is that in a couple of weeks, if you ask the same question for Google Images, our picture would come up before any other picture.
Oh, wow.
Right?
And like it was indexed by Google? That's what
it was indexed by Google. And the reason why is because many more people would be clicking on our image because there's an interest in generation than on the real image. And what Google's ranking system would basically say, well, if I ask you like, if I ask you for this prompt, and then more people click on this image than on this image, then this image gets upgraded. And so our image was at the very top. So we're very proud that we kind of, so it basically was showing that, the ranking systems, there's no reasoning, right? It's just indexing, right? And so,
yeah. What did the data labeling look like at that point? Like, was a lot of your time spent basically having somebody look at images and just describing them in natural language?
No, I think that there were a few data sets. There is something that's called Microsoft Coco, like big labs would label the images, and we would just basically try to either, I never spent time labeling the data. I think because like I was in machine learning, in machine learning kind of like, and so students in ML, they don't want to, students in computer vision, they kind of like tend to label more. We just rely on data sets and images that are coming from other labs. So we never labeled, but we were trying to basically build algorithms and try to identify, because it's kind of like, the fascinating field, the fascinating piece that we have right now is that people don't like hallucinations, right? Like people don't like when models hallucinate, because, it's generally bad. On the other hand, when we looked at computer vision, we actually do want model to hallucinate in the sense that we want models to produce something new, something that's not part of the training data. If they're able to produce something that's not part of the training data, then we believe that the model actually has some form of generalization. I remember there was this argument where we were looking at models like generative adversarial networks, GANs, and try to evaluate these models. And you look at GANs, these beautiful models, they would generate like very nice looking images. And then the question has always been, well, this particular image that it generated, is this like truly generated image? Or is it something that you kind of picked from the training set and just modified a little bit? And, because when we were looking at images, like one sort of great generative model would be to just pick a training example and show it to you. Right. So I ask you to generate me images of horses. I go to my training data, I pick images of horse, and I show it to you. Right. And if you as a user, you look at it, it's like, this is great, right? These are true images of horses, but it's meaningless. Right. So we were sort of trying to test, can it generate different variations of the horses? Can it generate different viewpoints, different backgrounds? So does the model really sort of understand pieces? And then you started getting into these problems where even for image recognition tasks, if you're trying to recognize cows, early versions, the model would do really good at recognizing a cow, right? But then if you put the cow on the beach and you try to ask system, what is this? The model would start confusing these cows with like boats, right?
Or it's kind of like when people always use the example of like a chihuahua with a bunch of blueberry muffins.
Yeah. That's one example. That's right. And so like it's a sort of like, and then part of it is because, when you look at cows, they're usually like in the grass fields, and, like you never see cows on the beach. All right. So if I artificially put cow on the beach and I ask them, well, what is this? Like it will start confusing. And so this was like one of the early failure points. And, right now people sort of can handle this. So right now vision systems are getting to the point where like really, really well, they work remarkably well, even compared to like, to human accuracies.
Yeah. So let's go to like 2015. So you started a company called Perceptual Machines.
Yes.
So what was the genesis of that business?
So we basically, it's interesting because, at the time I couldn't talk about this, but myself and a couple of my students, Nitish Srivastava and Charlie Tang, we started the company looking at detection systems. So early on at the time, people were looking, how well can you detect objects in images? And at the time, it started working well enough that the systems could actually do well. Right before it was, after AlexNet paper, classification started working. People started looking at sort of detection, and detection was one of these sort of challenges where I want to be able to look at the image and just say like, oh, there's like 5 people here. This is the way we are. This is the way they are. This is a car. This is where it is, and such. And we started working with Apple. At the time, Apple was also looking at autonomy and sort of like trying to build strong computer vision systems. And we started working with them, and I think that eventually we sold the company to Apple, but it was interesting because, at the time, a lot of work was done using traditional computer vision techniques. And it was very clear that the new wave of deep learning models was just much better than whatever traditional computer vision techniques could do, right?
And what was that new technique?
This deep learning based. So these were
like CNNs or
like there was CNNs, these are ConvNets. There were like multiple layers, learning multiple layers of representation, specific loss functions, detection loss functions, whereas traditional computer vision techniques were based on like, well, let's find a bunch of features, hand design those features, build some kind of like linear models, build like support vector machines, and and then like these are kind of like very kind of arcane sort of systems, whereas these deep learning system, ConvNet systems, started working well enough that when you learn them at scale, they showed way stronger performance than whatever was happening, right? And so then we started working with Apple and showed that this technology was way better than whatever they were doing. And so it was making sense for us to go and work. And I spent 3 years at Apple with a team. We were working on autonomy. At the time,
autonomous cars?
Autonomous cars with a project called Project Titan. And so this was, we essentially were building the perception stack, like early version of perception stack, like, recognize objects and images and so forth, right? So this was pretty cool, very cool application. And of course, it goes far beyond that. There is other parts of the stack and actually, but the perception system, the initial perception system was based on deep learning, and it's sort of
Sorry.
Yeah. No, go ahead. Yeah.
Yeah, I was gonna say, so early on, so with self-driving cars, basically the unlock was, hey, now we can actually recognize what's going on in front of the car, and so we can use that to actually maneuver the car. Is that basically okay?
That's exactly right. So
why did?
Yeah,
sorry, go ahead.
No, go ahead.
I was gonna say like, yeah. So yeah, it seems like around that time there was a lot of interest in self-driving cars. It seems like then for a few years it kind of went nowhere. And then basically in the last couple of years, things have picked back up, and now cars can actually full self-drive themselves. So like what changed?
I think that what was happening, so the whole sort of self-driving business started in 2015, 2016, right? And what happened with self-driving cars and with technology like perception started working way better. And what happened is that we went from 0 to like 80% in a span of like a year or 2 years.
What did 80% look like?
It's sort of like, like let's say you sit in the car, right? You can detect like most of the objects. You can detect cars, you can detect pedestrians, you can detect the road and sort of like, but then you started hitting corner cases, right? One famous example was by Google, because they were the first in this business, is that there was like a bag flying on the highway and the model just recognized it as like some object, didn't know what it was, and start slamming on the brakes, right? In the middle of the highway, right? Like, or there was another example where towards like end of spring, vegetation started like, like from the trees, and the systems that would look at perception, looked at the LiDAR and everything would basically say, there's like some objects that's occluding kind of like my path. So I can't go through that, even though it was just like a bunch of bushes kind of like, over kind of. And so what I mean by from 0 to 80 is like basic stuff was there. And then you started hitting these corner cases. Construction, like people start putting cones or like something, on the road, right? And that's what basically stopped a lot. So it was a lot of excitement because like even in the early days, I think people were basically saying, okay, in 2 years, we're just going to have full self-driving cars. People were now studying reports, what's going to happen to truck drivers, what's going to happen to taxi drivers within the next 2 to 3 years, like the whole economy is going to change, right? So people were like very sort of, feels a little bit like AGI we have right now. People say AGI is 2 years, and people who actually work in these labs and frontier labs, I know a lot of them, they basically saying just like, we're not going to have AGI in 2 years. So I think there was excitement in self-driving cars is like, look, in 2 years, we're going to have full self-driving cars everywhere. The other corner cases that started picking up is weather, snow, like all these other things, right? And perception is one part of it. Like then planning, how do you plan things, right? Like for example, now Waymo has a way of actually being a little bit aggressive. Like early versions of these cars, like you couldn't merge into the highway because there was a lot of safety things. So you try to merge in the highway and just people just don't let you merge, right? Because that's how we drive. If you're slow and you don't, you're not aggressive enough, just nobody lets you in. And so they just couldn't merge, if there were cars. And the way that humans do it is they basically like, well, I'm going to go, right? And whoever is behind me will have to stop because otherwise, and so we kind of adapt to this, right? And early version systems could not. And so they were just not, and so the whole field was stuck for about 4 or 5 years, primarily because of these corner cases and like all the nuances, right? And even today you have way more, even today, you see like corner cases happening. And even today, they're expanding to cities, but this expansion is very slow. Part of it because you have to have high definition maps. You have to sort of know exactly what the road structure is and everything. So it's not like you have a system, you just turn it on and it just works anywhere.
But it seems like Tesla FSD can basically run everywhere because like I've rented it and I've gone to different cities and it just works.
It works, yes. But with Tesla FSD, it's a great sort of system. But at the same time, with the self-driving cars, being 99 correct is not good enough. I think that's one of the things that, it's interesting because I think that the technology could save a lot of lives. Right now, when I'm in San Francisco and I drive on Waymo, I feel safer than when I have an Uber driver. Like, I've driven multiple times.
I agree.
But at the same time, there is this sort of argument that, 99.9% is just not good enough, because if you get into the accident, that's, Uber had one accident and they've shut down their entire kind of like operations, right?
Yeah. What changed since like, 2017, 2018 to now where, okay, we were at 80%, now we're at 99%. Sure, we still have that, 0.99% to go maybe, but like what allowed that,
I think it's just
dramatic increase?
I think it's just the data collection and continuous improving of the models.
Okay.
Obviously, Waymo has LiDAR, so they look at the cameras, they're running deep learning models on the cameras. Some of the architectures might have changed. Maybe we went through CNN's convolutional neural nets to transformer-based architectures. There's a few sort of nuances. These are hybrid systems, and Tesla FSD is still relying on, I think, CNNs and transformers. Low-level processing happening with CNNs. The high-level processing happens with transformer-based architectures. I mean, LLMs are based on that. I think it's just, to train these models, you need a lot of data and you need a lot of corner cases, right?
Yeah. Which I guess Tesla has a lot of because they just have cars driving all over the place.
Yes, exactly. Yeah. Cars driving all over the place. I think they're very well positioned to just because of the amount of data that they have. On the other hand, what, like right now, with taxi cabs, like what Tesla is doing, like just having cars without wheels, that's going to be the final frontier, right? So like right now you sit in your Tesla and you still kind of like, you have to control what you still have to be in the car. Like
like at the very end, like when you get to your parking lot, then it kind of messes up sometimes. Yeah.
Yeah. So it's not like, and then, truck industry is the same sort of, but at the same time, like you still have to be at the wheel. The question is, when are we going to get to the point where there's no wheel in the car? You just sit the back of the car and you just don't even need to worry about, so that's, that's going to take some time, but,
Yeah. Do you think there's going to be something like an iOS versus Android thing where every other company that wants a full self-driving system will basically will work together to do it because they have way more cars compared to Tesla?
Yeah, it's a good question. I don't know. I think
Okay.
every car manufacturer is trying to look into this, but I suspect, Google's business is probably going to be they'll develop the tech. The only problem with Google, to be honest, is that right now the economics is not working out just because they have so many sensors, LiDAR, and everything. When something breaks, they have to maintain it, and it's just when something goes wrong, you have to maintain it. So you're kind of like right now, it's more expensive to have self-driving cars than just having a person driving a car, right? So
Yeah.
but at some point it will kind of break even, and then it's but I do think that essentially all cars in the future are going to be self-driving cars, and there's probably like somebody like Google or Tesla, whoever is building that tech will build in such a way that can be integrated into any other car.
I see.
So
I'm actually just curious about the architecture of the neural net that's like running FSD. I don't know if you know much, or maybe you can try to guess.
yeah, I can try to
But
guess. I don't know what
yeah,
FSD is doing, but I suspect they're doing some form of CNN plus transformer-based architecture, like CNN for the low-level processing, plus some form of transformer architecture that kind of like synthesizes a bunch of different sensors. And I suspect a lot of, Waymo, for example, what they're doing is that, it's a hybrid system. So it's not, people typically think, well, deep learning system, like images come in and then actions come out, like how much you should steer the wheel and such. There are some companies like Wave, I think, that are trying to do that. But what way more and more serious companies are doing is they basically taking all the input and then creating a 3D map of the environment. They know exactly where the cars are. They know exactly what the roads, they know exactly how far these cars are moving. And then there is something that's called a planning module. A planner basically replans, like I think at 8 times a second. And it sort of tries to say like, okay, should I stay? If I'm trying to change the lane, what path should I take? What sequence of actions should I take? So it's almost like, sensors give you a 3D representation of what's happening around you. And then you have a planner that's actually saying like, okay, changing lanes. So if I need to go faster, or if I see the red light, I need to stop. All of that is happening on top of that representation.
I see.
Right.
Interesting. And
Right.
then like how like is it basically they have like multiple decoders or something that are working together? Because like how do you sync up the steering wheel along with the gas pedal along with the blinkers?
Yeah. So they
Yeah.
basically have some form of motion, like something's called what is it? MPC. This is kind of like predictive control systems, where all the sensors sort of come in, and then you have a policy that tells you exactly what the wheel configuration should be, what the gas configuration should be, and like all the other sort of, So it's essentially a policy that spits out actions. And these actions would be, composition of steering wheel, pedal on the gas, or brakes and such. So I think that the critical piece is perception, and that's why you have LiDARs. And, Tesla doesn't, because Tesla believes we just have cameras. But Tesla sort of was doing it. To me, I believe the more sensors you have, the better, because you can kind of like observe the world around you better. But LiDAR just looks ugly. You
Mm.
cannot sell cars with LiDARs. And so like Tesla could not afford, like, it just looked so ugly, right? So they
Is
kind of,
LiDAR really expensive as well? I don't know the
LiDAR is
prices.
expensive. The prices are going down, but it is expensive. But it's this thing that sort of like sits
Yeah,
off, and like, it spins, and it's
yeah.
just like nobody would buy a car. Like I would never buy a car with like bunch of LiDARs. Like it just looks ugly, right? It's just, so Tesla had to go with a vision only, because that's the only way. Waymo
Interesting.
took a different path. Waymo basically said, we're gonna put all the sensors, because that allows us to be more precise around what objects around you, right? I
Yeah.
can really tell you there's a car here. I don't need computer vision techniques to detect and understand. I know there's a car, because you have these lasers bouncing around and sort of
Yeah.
telling you where things are. So, and of course, if your goal is to design a cab that just something that comes to you, picks you up, and drives you from point A to point B, you probably don't care if it has ladders and whatnot, right?
Yeah.
But if I want to own the car, I don't want it. It's like expensive. It breaks. It's, so it's interesting to see like, two different viewpoints. One is just vision based. The other one is like more sensor based.
Yeah. Interesting. So after Perceptual Labs, you went back to be a professor
At
at
CMU,
CMU.
yes.
Yeah.
Right.
And then you joined Meta Superintelligence Lab. Why did you join initially?
Yeah, so this is kind of like interesting, because like one of the projects that we're working at CMU on, and we continue working on right now, is what we call computer agents.
What
And
year
so
was this, by the way?
this was 2022.
when you joined Meta?
No, I joined the Meta in 2024.
Okay. So you were at
So
CMU in 22.
2022, yes,
Okay.
I was at CMU since 2020. Well, actually, I was at CMU but I was at Apple during that time, so I came back to CMU. And in 2022, 2023, we started looking at these agentic systems. When ChatGPT came out, it was kind of like amazing what it could do at a time. So we started looking with a student. His name is J.Y. Koch. He was at Google before. He's doing a PhD with me and another professor, Daniel Fried. And so we started looking at building agentic systems because the thinking was that, well, early on, if you have an agent that can sort of do things on your behalf, that would be interesting. And so there was a research, there's a lot of research happening at CMU. One of the things that we were looking at is we were looking at these multimodal systems because we always were looking at combining images and text and actions. So we've built something that's called Visual Web Arena. A bunch of students at CMU, and this was one of the early systems that you give it a task like, hey, find me the cheapest iPhone on like Craigslist, and make a posting offering $20 less than the asking price. And so the system would have to sort of navigate to the appropriate web pages, find the right information, try to compare what's happening, what's the cheapest price, or what's the right thing, and then, post the message. And so you can kind of like autonomously trying to solve these tasks. So we built this simulation environment that simulates Amazon, simulates Craigslist, simulates Reddit with some of the tasks. I think we had in about 1,000 tasks, 950 tasks that we've designed ourselves. And we sort of started building this environment and, building these agentic systems. And at the time, we got an interest from Microsoft and Meta. So we went to Microsoft. We've talked to the Microsoft folks. They were very excited. And it's at the same time, we started talking to Meta. And Meta at the time, they were open sourcing their models. So that was a big appeal to us, like early versions of Llama models. At the time, they were coming up with Llama 2, Llama 3, and they were like fully open sourcing for everybody to use. And, Llama 3 was a great model. And so it was making sense for us to say, okay, well, if they're open sourcing everything, from our perspective, it was pretty cool environment to go and try to build some of these agentic systems inside a bigger lab because they had more compute, more data, more infrastructure for training these models. So
why was them building open source models really interesting to you?
I think it's because being in academia, most of my students were using Llama 3.
Oh, I see.
And Llama 2. Right. And this was like, okay, well, if we go and build some of the agentic systems, like if they open sourcing it, then it's kind of like helps us as academics. It helps kind of like also for us, we're not constrained. We would publish the findings and, and I think that was appealing to me. It was appealing to students. And so, we started working with, we actually joined Meta and spent a couple of years at Meta.
Yeah. So you guys were building like early computer use models, basically.
That's right. We were building early computer use models.
So like even now,
yeah.
Sorry, go ahead.
There was a team that's also was looking at that. So we were, we were joining forces and sort of like trying to source the right sort of data because like for computer use, web navigation, you need a lot of grounding data. You need a lot of kind of data to teach the model how to click on things, how to, and so, yeah.
And now that's like a big business. It seems like everyone wants to build RL environments.
Yes, that's actually, yes. But right now with Code Cloud, building these RL environments becomes a little bit easier. I mean, right now in my lab, like after we left CMU, in my lab, we continue building some of these models. We've built an environment called Odysseys, which is sort of an environment. I mean, it's not an environment, but it's more like a task where I give you very complex tasks that would require, a human a few hours to solve. And sort of now we're progressing from sort of simpler tasks that we were doing before to more complex tasks that would, again, require you many hours. And there's something that we call long horizon tasks, where the system actually has to go do research, find information, and sort of do the right sort of planning and such.
Yeah. So like what were some of the early challenges that you guys had to solve when you were building those computer use models? Because even now, I feel like computer use models, like
it's still early. It's still early.
Yeah. It's not, they're not amazing compared to the LLMs, for example. Yeah.
No. And I think that's what makes it exciting because, obviously these models, the thing with these models, with computer use models, there's like terminal aspect of it, where like through MCP and such, where you can communicate with a particular website or a particular program through the specific protocol using LLMs. And then we're kind of like working and kind of don't. And there is this argument that if you're able to build a system that can control visual interface, would it be your computer, website, or whatever visual interface you have, because people are inherently visual and we sort of, then these models would be more general. One of the problems right now is that the models are not good enough at this point in terms of grounding, like clicking on the right things, because there's lots of things to do. And sometimes they fail on planning. So even frontier models today, on the other hand, they're getting to the point where you give them very, very, like, for example, one example that my students always sort of ask is that I'm graduating with my PhD. Like, I want to do postdoc, or I want to apply for faculty positions. Okay, which schools are looking for faculty positions? What are the deadlines? Are they looking in my area? What information I should be providing? And so, it's not a really hard task, but PhD students spend like a few days, right, trying to search, like, okay, Stanford looking for people. Oh, look at this. This website says, yes, they're going to be hiring people. What areas? Well, they're hiring in robotics. No, they're not hiring in machine learning, so maybe it's not for me. And sort of, and imagine you sort of, and so we've built these tasks where we ask the model to, say, okay, I'm trying to look for a faculty position, right? Give me the list, like go to the top 25 schools in the US, try to find whom are they hiring, what are the deadlines, make me Excel spreadsheet with all this information, and you give it precise kind of like what it needs to collect. And also, so that it doesn't hallucinate, actually go on the website, verify that it's correct, and keep it open as a tab for me, so that if I'm interested, I can go and actually look at it myself, right? So it doesn't, because sometimes the models would just say like, yeah,
I did it.
I did
But
it,
then you
right?
ask it.
And then like, where is this? Like, I don't
Did
know.
you
where
really
this
do
is
it?
coming.
Sorry, I didn't actually do it.
Yes, exactly. So these are computer use tasks because it actually requires you to go on the web and like open the thing and, like so that I can actually see, not just like, hey, Stanford says that they're looking for people and this, like, but you actually go, open the link yourself, look at the link and keep the tab for me so that I can, verify it myself. So it requires to actually engage with your computer. And the way that we've done it, actually, we've asked a bunch of people to provide us with their history. We paid the people to provide like what are they doing on computers, what are they using them for, and so this was kind of like inspiration for us to build some of these environments, some of these data sets. It's still early on because we're still trying to understand what people are using. One sort of success story is the OpenClaw, where people sort of like figure it out and giving access to people how people want to use it. And people want to do a lot of different things. People want to hook up your LLM into your sound system and do stuff. And then so it's one of those things that people are using computers for a lot of different things, but it's very hard to know exactly what they want to do it and how much they want to automate. I can give you one example. There's a wonderful company called Utori that does web navigation, like agentic systems that kind of like go over the web. And I think when somebody was telling me that some of the early use cases was when people buy something, they want to look for coupons. So it's like, I'm buying these shoes. Hey, agent, go find me coupons. Find me 20% discount. Who's selling these shoes at 20% discount? It takes me an hour and it comes back and says, hey, you can buy these shoes over here. And with this coupon, you get 20% discount. Hey, I'm going to use this product.
Yeah.
So it's like, it's not like safety critical thing because maybe there is a discount, but if I didn't find it, I'm like, okay, fine. But if it does,
I was going to buy it anyway. Yeah.
Yeah, I was going to buy it anyway. Like, so these things you kind of like, you start seeing where people, but it's still early. It's still early.
Yeah.
It's not robust enough where you can sort of just delegate the task and say like, go do it. And then
like one use case that I was working on with computer use agents was we were working with this company where they have like an online marketplace of courses. And what they wanted was they wanted an agent that they have like 8,000 courses and they wanted an agent where you could give it a list of the course links. And then the agent would literally like go and take the course. So it would watch the tutorial videos. It would answer the quiz questions. It would download the homework assignments. And then the reason why they wanted it was number one, they wanted to basically download the assets. So then they could standardize the course outlines for all 8,000 courses because they were just made by random people. So it wasn't standardized. So that was number one. And then number two was they wanted to take screenshots of the course so that they could generate an accessibility report that, hey, like for people who are for people who are deaf, like you need to have captions on the videos. So, you know, does it pass that rule? Does it not pass this rule?
Yeah, no,
Et cetera,
these
et
are
cetera.
excellent. These are excellent.
And
Yeah.
we tried using like the Google computer use model, but maybe we just didn't spend enough time on it, but it just didn't seem like it was like good enough. And so
yeah, I think
basically go ahead.
Yeah, I think that existing models are not at the point where you can sort of like reliably rely on them to go and do these kinds of tasks.
Yeah.
And these are kind of like difficult tasks, right? Because that it requires you to understand both the textual input, like HTML or whatever the behind, but it also requires you to have very good grounding, right? Like understanding what's on the website, what are being displayed, and you know, so it's sort of these multimodal models are still sort of. I think they'll get better. But
Yeah.
there's a bunch of startups that are also trying to build better multimodal models. But yeah,
like what makes them better? Is it not just more data, or you have to have like a different architecture? Like what is
that's
it?
a good question. I think since 2002, when we're building these models to where we are right now, it's night and day. Right. So frontier models now actually, you know, GPTs and Gemini and Claude, the latest models are actually pretty decent. Decent in terms of like the performance has improved dramatically. It's still not at the point where you can trust them completely to just go do the task. Like, you know, I can ask you like, you know, like here's the task, go do it. And I know, you know, a capable person will go and do it. Like a good sort of engineer will go and do it. You can't unfortunately do it with existing models.
Yeah.
Right. So kind of like have to, you know, and so people are building harness. I think it's going to take a little bit of time, but I think that's an interesting research. From research perspective, we're trying to understand. So for example, we also did this analysis of the frontier models where they fail. A lot of times, for example, you know, GPT does very good planning of what it needs to do, how it needs to do it, and then it just doesn't do it. So like, okay, it's like done, I can't do it. Opus, for example, does a lot of research and is doing, but then sort of forgets to replan and such, gets lost, and then like kind of, especially for these long kind of like tasks where you have to do a lot of different things, it sort of just forgets or doesn't plan. So like, again, we have these benchmark odysseys, and then the best models hit like 60% or like maybe 65%. And you need to have like, you know, above 99.9% for them to be like, for me to be reliable to say like, hey, go do it, and knowing that they'll go and do it. So yeah, there's still some.
Yeah.
Also, another interesting work on like computer use agents for controlling your phones. You know, like if I give certain commands and cross the apps, and like there's also no notion of personalization. So if the agent knows a lot about myself, you know, my apps are cross-connected. Again, this is something that we're trying to build to test how well existing models are doing. We have something called iOS benchmark, which is sort of mimics iPhone and the apps on the iPhone. And it's this notion that if it's my phone, you know, when I order Uber, right, I can go on Uber map and see when my food's going to arrive. Then I can go to my banking app and see like, hey, did they charge me the right amount or not, right?
What's different about building computer use agents for your phone versus just a normal desktop?
I think that they're very similar. The set of actions is different. Like in one case, you're swiping and such. Visually, they look different, but they're pretty much the same systems. I think that sometimes also like a lot of existing benchmarks on computer use are kind of like these generic things, like go to the CAT system, look at the video game, you know, control this and such. For the phone and maybe for your personal computer, there is this notion of, again, I think the notion of personalization, right? My phone, you know, I have Slack, I have my email, I have my banking, I have my flights. They're all kind of like interconnected, right?
Yeah.
There's this good example. I think I really like this example that Apple gave, I think a year and a half ago, when they were talking about talking about intelligence, like Apple Intelligence, which really resonated with me, which is they basically said, hey, simple question. I'm going to ask Siri, you know, when should I go and pick up my mom from the airport? What, you know, San Francisco airport today? A smart system would basically go through your emails and find the flight that your mother is on. Let's say it's whatever the flight is, look at this flight, go to the airport, see if the flight is on time or delayed, right? If it's delayed by 1 hour, estimate when the flight's going to land. Look at where you are, open the Google or the Apple or Google Apple Maps, and look at like how long is it going to take you from the airport from your current place to the airport. Usually if there's a lot of traffic, estimate what the time should be, and then basically give a simple answer. Okay, you should leave your home by 2:15, and then sort of say, well, the flight isn't thing, but it's delayed by 1 hour, also the kind of traffic conditions are like these. We'd expect these to be worse in an hour because that's the traffic patterns and you kind of like see because that's the path that you're traveling. And so now an intelligent system, a dumb system would basically say like, oh yeah, flight lands at like 12 o'clock. That's what's in the email. So you figure out when you should get there, right? And intelligent, and you kind of like don't even think about this, but that sort of requires you to, like you open your email, figure out when the flight. Once you know what the flight, you have to go to the airport's website, sees the flight delayed, right? Because they kind of like listing, or is it on time? Is it really on time? Because a lot of times flights get delayed. Go open the map, see what the traffic conditions are. Like, so this is sort of gives it like a very interesting sort of, basic intelligence, right? Like,
yeah, interesting. What were some surprising things that you came across when you were at Meta about training models at that level of scale?
one interesting thing that I came out of, and it's true of all the frontier labs, is that the architectural choices are very similar, like similar to the original transform architecture. I mean, there's a few nuances and everything, but the main sort of effort is engineering and data, infrastructure, engineering, and data. It's kind of like, when GPT-5, when GPT-3 or GPT-4 came out, a lot of people were basically saying, my God, OpenAI has like figured out a new architecture. They figured out like AGI. They figured out like a new sort of thing that nobody else knows about. That's absolutely not true. The architectures are the same. These are transformer-based architectures. Everything comes down to the data, the quality of the data, engineering, infrastructure. How do you do reinforcement learning? I think that, the breakthrough like in reasoning systems was a good one. But when you look at these architectures and such, it's fairly standard. So, and obviously like there is a lot of work on self-improving systems. These are all fascinating systems, but a lot of them are sort of, I guess what I'm trying to say is that it's fascinating what's been happening. But the real drive has been more on the infrastructure, the data.
Yeah.
The way that Claude is actually working, it's fascinating because it's almost like a game in the sense that I give you the task. I have my code base. I have my unit tests. And if the model is able to pass all the unit tests, I give it a reward of 1. And I use reinforcement learning to reinforce whatever I did is the correct thing to do. And then what you can do is you can basically say, well, what I'm going to do is I'm going to introduce subtle bugs manually myself through combination and such. And then that's another training example. Now my agent has to go try to fix it. And if it fixes, I have unit tests. And that's like, it's almost like a game where I run the thing, I get the score. And I always know whether I fixed it or not. Right? And so it's not like with web agents and sort of like computer use, sometimes I can solve the same problem many different ways. And sometimes it's like partial solutions are also okay. But in the systems like math and coding that's why we were seeing a lot of progress, is that these are kind of what we call verifiable domains where I did a task. There is one, like, I know where I got the answer correct.
Yeah.
So,
do you think we're at a point where that is plateauing, where just the amount of data is not actually improving the outcomes as much as they were 2 years ago?
But what's interesting right now is that there is sort of, the continuation of this piece where you sort of try to generate synthetic data. Right. So in coding, you try to introduce bugs, artificial bugs, and get the system to fix those bugs. And you kind of like continuously self-improve the system. I think that the self-improving aspect of it is an interesting one because you can kind of introduce like disturbances in the system and then try to fix it. There's a lot of work also on synthetic data generation. A lot of times, you have multiple models, they all generate data and you kind of like clean it up, you pass it through the filters and say, now use that data for training. So there's kind of like many, many nuances. I don't know whether we've reached completely the scaling law kind of like saturation where we basically say we've done, because I've been wrong before, like where people would say, well, scale is not going to get you far, but scale is getting you very far, right? Like all the innovations that we had so far is due to scale of the data, right? And these sort of like emerging behaviors. And of course, you need to sort of make sure that, and then if you have strong models, you can sort of generate synthetic data from those models, filter them, and that now becomes a cleaner training data for your model. So I don't know. I don't know. I do see the appeal of multimodal data where you go beyond language. You go into the physical world. This is where robotics applications are now happening, embodied AI. where in addition to language, you have videos, you have world models, you have like these other rich sources of data. I have one of my former students who's a professor at MIT right now, Paul Liang, was working on multi-sensory foundational models. So for example, he's now working on building models for smell, right?
Interesting.
Like, can I like, if I have my senses smelling, can I understand what am I smelling? Right. And, like touch senses, if I'm touching something, can I identify like without vision, like, am I touching specific type of, so you can imagine there's like many, many more different areas. It's just the industry right now is focused on images and text, videos as well, because for companies like, Facebook, generating images, like one of the success stories of Gemini is not a banana, apparently. Like
that killed our business when we first started.
Yeah, this
we
is
were
like
we were
so
doing
good.
like virtual try-ons for like retailers, and then Nano Banana comes out, and you can basically do that with one API call.
Yes, exactly.
Yeah.
And it's like, it just became very popular because like, I have a friend and he's like, my dad is in his 70s and he's like using Nana Banana for like push himself into some weird kind of like, situations, and then sends it to his family, to his friends. And it's like, oh, and everybody's like using it, right? But there's obviously like much more beyond just images, right? There is videos, there is sort of understanding the physical world, and this is where robotics will have to face this, right? I mean, self-driving cars is kind of, one aspect of it. But of course, for businesses, I mean, Claude is an amazing product. Like, I mean, I'm using it. All my students are using it. Anytime I have a bug somewhere, just give it to Claude and it tells me like, oh, you have, you don't have the latest version of Python. Like, do you want me to install it for you? I'm like, sure, go ahead. And it's like pip install, whatever the commands that I would basically spend lots of time doing, it just does it for me, right? So
yeah. What are your thoughts on the future of software engineering? Because like most of the engineers that I know, they're basically saying what you're saying, where I haven't written a line of code in months, is what I keep hearing.
That's true. But at the same time, I think that you still need to have good understanding of software engineering and how things work. Because if you actually have to go and debug it, you have to be good at it. But of course, like, you need to understand how to use AI tools as well. So I think in the future is going to be some kind of hybrid, but I would not recommend people to sort of like say, well, don't do coding or completely abandon coding. I mean, there is an argument for that. Like when I was doing my undergrad, we were studying assembly. Hey, this instruction, inject this bit over here and then this bit over here. And like, I don't know, like nobody's doing assembly, right? Like it's fully kind of, but at the same time, if I had to, I could go and like figure stuff out if I needed to, right? I think that pure software engineering is probably not going to be the thing, like where you're just a coder. I think people with strong machine learning statistics kind of expertise plus strong coding expertise is what's going to be in demand.
So basically, like research roles is basically what's left.
Research or research engineers, like engineering, pure engineering. Like, I mean, yes, obviously you have amazing people who can optimize and everything, but people who understand how these models work with strong coding skills, I think will continue being in demand.
Interesting.
Right.
So
because
you think like,
yeah,
would you say like most software engineering roles are not that right now? And so do you believe that those roles are going to go away?
that's a tough question. That's a tough question. I think that, some of these roles will stay, but I think that what I see happening right now with a lot of businesses is that instead of having like 10, 10, computer programmers, I only need 5 or 4 or 3, right? Now, of course, like, I mean, it sort of makes the whole thing more efficient for sure. It also makes kind of like some of the research that I'm seeing like faster, because I can give you an example. One of my students is, like they're running experiments and they found like coding agents to be extremely useful. Like if something happens overnight and, it fails, the agent can go analyze the error and say, the memory wasn't set up properly. Let me increase the memory and start running it again.
Yeah.
It's extremely useful because, you've just wasted 6-7 hours of GPUs if it just sits there, right? And so
I actually just did that like last night.
That's
literally that.
exactly. And so it now becomes extremely, and so I think that, it's a good question. I don't know. There's a lot of software engineers. People are still looking for strong software engineers, like everywhere. Even in my company right now, there's always demand for like, we've hired a person who's like amazing engineer, but also very strong machine learning person. So those people are always going to be in demand because, it's not just like we say like, hey, go fix this thing. The person goes, fixes this. The person actually fixes and then comes back and says, I think you're doing this wrong. Like we should do it differently, right? Those people are going to be in always high demand.
Yeah. People with the judgment, essentially.
People with judgments, people with understanding of machine learning, AI, but also strong coders.
Yeah.
Right. That's
okay.
kind of...
Yeah. So maybe that leads us to like you starting Sooth Labs. So could you explain what was the genesis of Sooth?
Yeah. So
you left Meta.
Yes, I left Meta and I started the company with a couple of co-founders. One of them is Yasser Sheikh. He was a former professor at CMU. I've known him for a long time. He also he was at Meta for 10 years, building some of the Oculus and some of the predictive models, like how people behave and such. And so the premise for Sooth Labs is we want to be able to build a foresight system, a system that can forecast future events, or at least estimate, create what we call calibrated probabilities for future events. So you can imagine that the system that basically takes all the available information today, this would include some structured data, which is like time series, like, new reports, earnings reports, or maybe like unemployment rates, right? Like things of that, and then combining it with unstructured data, news, things that are happening in the environment, right? And whatever that information is, you can fuse it together to try to forecast certain probabilities of certain events that might be coming up. I can give you an example, perhaps a toy example.
Yeah.
So I have a student. Hopefully he's going to be okay, me giving this example. He's a great student. He's like one of my best students. His name is Martin Ma. He's working on, multimodal aspects, and I'm co-advising him with another professor, but he's working on multimodal aspects and such. And so he's graduating in December. So I was talking to him what he wants to do next. And I said like, hey, look, we're building this sort of agentic systems for forecast. Let's ask the following question. Will Martin Ma, CMU student, graduate by December 2016. So the system finds him and says like, well, Martin Marr, PhD CMU student, a PhD student at CMU who's been there for 4 years, graduate by December 2026. So it formulates the question, creates a contract, much like what you would do in Polymarket or Kalshi. Like, this is the thing, this is how we're going to resolve it. That's the question. So the model goes through reasoning. It thinks about, what's the probability of this event occurring. Comes up with the answer of 13%, 13%. Basically saying no way he's going to graduate by December. Mm-hmm. So it was like, that's surprising. Why is it so low? So you go to the system provides reasoning, like what it found and what's the reasoning behind it. And it basically says, well, Martin hasn't proposed yet, which is true. He hasn't done his thesis proposal yet. He was going to do his thesis proposal a couple of weeks after. And the system answered, okay, that's fine. A lot of students, propose later. And then it said, well, and there is a new requirement that was introduced in the department. So it found a document through sort of research that there is a rule right now at CMU that the time between your proposed date and your defense date should be at least 12 months. So it starts doing reasoning and basically saying, well, you haven't proposed. It's May. You try to defend in June. There's a rule that says like the time should be at least 12 months. That means that your probability of defending goes down significantly. So I'm asking Martin, did you know about this rule? That's something new that they've done. And the reason why CMU's done it is that a lot of times students would like propose and then 3 months defend. And that wasn't the intention. The intention for students to propose like, what they've done, what they're going to do. And the committee like looks at them and says like, okay, this is what you're going to do in the next year and for your defense and such. It was designed specifically to avoid situations where people just sort of, try to, and he said, yes, I know about this rule. And then the model would basically generate what we call like trigger events, or what we call like decision points. And one of the decision points was that Martin gets a waiver. So in the next month, there's some probability that you will get a waiver. Condition on this event that you get a waiver, your probability of defense goes up from 13% to something like 80%. So I'm telling Martin, like, have you thought about getting your waiver? Like, for this thing. He's like, yeah, I should probably get a waiver. And I'm like, yeah, you probably should. If you want to graduate, you probably should go get a waiver because otherwise you're not graduating, right? So this is a little bit of a toy example, but you can imagine that a system that forecasts any future that from will Anthropic IPO this year? Will SpaceX go to Mars by 2030, right? Any sort of question, we believe that right now, I mean, there are forecasters, there's something called super forecasters, which is the people who have a deep knowledge of certain areas, and then they try to estimate the probability of future events. Of course, nobody can be precise of saying whether events happen or not, but you can estimate the probability. And calibrated estimation basically means that, if the system says 70%, then out of 100 events with 70%, we'd expect 70 of them to happen and 30 of them not to happen, right? That's the meaning of the calibrated probabilities. And so we believe that, in this sort of vertical, AI should be able to do much better than people. And then I think it will open up a lot of these decision points. So it's not just the outcome, but it's like a lot of decision points, like, certain things you can influence, certain things you can't. Like in Martin's case, like he actually went and got his waiver. Mm-hmm. So he basically said, okay, if I'm trying to optimize me graduating, like these are things that I have to do, right? And the system can sort of find and suggest. And it has a lot of implications because I think that a lot of times our world is like very interconnected. So things, geopolitics impacts, culture, and culture impacts how we operate, and sort of like all these things are very much intertwined. And right now, with the power of AI, how much data it can process in real time, this I think is going to be the next frontier. Mm-hmm. So we went from agentic systems that are super useful to systems that can kind of like look into the future a little bit better, given all the information we have today, and also try to kind of like make it part of the decision making. So if I am a CEO of a company and I have a better view of the future than my competitor, I'm going to win.
Yeah. So why can't I just kick off a deep research assignment in ChatGPT to try to predict something?
You can.
Okay.
The caveat is that these models like ChatGPT, first of all, they don't really take structured data into account. They're very bad at processing numeric data. It's number one. And these models have been trained to predict the next token, right? They sort of like, they're not designed to sort of predict. They're not designed for forecasting. Mm. They're forming like fantastic base models, but you still need to post-train such that you can adjust and such. And then there is another thing, which is accumulation, which makes this problem actually a little different, is the context accumulation. Which sources I'm relying on, which sources I should use, which sources I shouldn't use, which ones I trust, which ones I don't trust. And so it requires, obviously ChatGPT I can ask it like, will Martin Ma graduate in 2027? We'll come up with something, but I don't think it will do a good job at like giving me the reasons and giving me these sort of like decision points along the way.
So as much as you're able to talk about it, I guess, is this more of a model training problem or is this like a harness problem?
Both.
Okay.
You need to train your own model because training becomes a critical aspect for actually steering these models, not just towards predicting the next token, but actually trying to predict future outcomes. Right. So it's the training, but harness is also kind of, obviously you can rely on existing models as well. And one sort of interesting aspect of it is that, for example, Grok has access to Twitter. No other models have access to Twitter. Twitter sometimes is a very good source of the news, right? So if you're relying on ChatGPT alone, I think you're always going to be inferior. Just in terms of the ability to find and retrieve the relevant content. When you're also building these systems, I think for businesses and such, a lot of times corporations will have their own private data that they're accumulating and such. And so how do you build systems that can also leverage internal data and such? So
yeah,
this is
so why did you pick this problem to work on?
I think that from high-level perspective, I think the next 2 years is going to be the year of agents. Self-improving agents that can go do research, agents that can go do like, scientific experiments and whatnot. After 2 years, I think it's going to shift towards decision-making systems. I want to optimize for my future. Like what should I do so that in 2 years I'm going to have this job, right? I want, so it's almost like there's this notion of personalization for corporations, this notion of trying to anticipate the future. So it's more like if you have a system that can predict the future, you can never predict the future like perfectly, right? But if you can kind of like, it's almost like it's like blurry, but if I can make it a little bit more precise, then I can make decisions. So it's no longer about like, hey, agent, go like find stuff for me or like do stuff. It's actually, okay, what decision I should take so that I'm optimizing for my own future outcomes.
Yeah. Are there certain types of events that you are optimizing your training for? Because I'm assuming what you're doing is you're doing some kind of back testing on events that happened in the past, and then you're using.
That's a fantastic point. And that's the point that's basically is so hard. This problem makes it so hard because back testing, I can go back test and publish a bunch of papers and say, look, my model is better. Nobody's going to trust me.
Why is that?
Because back testing, there's always leakage of information.
I see.
Like I can give an example. Like, we had a way of like trying to predict some outcomes of a sports game, right? And we were like searching through the sources in a way, constraining to only look at the sources before July 2025, right? We picked up this Wikipedia article. It says like, was stand by July 2025, like, and was one of the sources, and we could perfectly predict. We could perfectly predict the outcome of the game. And we're like, this is fantastic. Our model works. But what happened is that somebody went, modified this Wikipedia article with the outcome of the game. And the stamp was like still. So the model that was, the data that was stamped by July 2025 contained the data about 2026. Right. So then it's like, okay, yeah, I can tell in the backtest I'm doing like fantastic. It means nothing. Like the only way. And this is what makes kind of like these prediction systems interesting, because you cannot, there's no way to contaminate your data. There's no way to overfit the data. The only way, if I make a prediction, I have to wait and see, like, did it come out or not? And this is where it becomes an interesting problem because, like at Meta, I remember there was an example where the model would basically generate an answer to a particular coding question, and it would generate the comment section as well. And it's supposed to be the test point, like where we test the model, and the model would generate comments which were too precise to be true. Like the comments would be like, hey, John, like, I think we should fix this part, right? Okay. You look at the test example has the same comment. Hey, John, I think we should fix this part, right? So what happened is that somehow this example actually ended up somewhere on the web. People scraped it, trained on it, and now we're testing. So we're testing on the training basically, right? So
wow.
This is known as the contamination problem. It's a big problem. It's not just, it's also frontier labs because, there was this example of TXZ unicorns where it's like people can say, hey, look, like if I prompt my model, it generates me these TXZ unicorns, like, and it's like, it's truly generalizable until somebody found that there is like an entire web page dedicated to this problem and has like all the examples. And so you kind of, it's almost like you're testing on the training, right? Which is not. But if you're trying to test on the future events that haven't happened, there is no way for you to cheat, right?
Yeah.
Like, it's just, and this is like true generalization, right? And that's what makes this problem very hard because there is a time component to it. Any sort of back testing you can do, okay, that's fine for model development and everything, it's okay. But to really test it, you have to do forward testing. And, like Polymarket and Kalshi is the way to sort of,
yeah. So I guess, does that mean that you will be building your own hedge fund then using this?
I think that hedge fund is sort of fairly narrow application because, if it works, it will have a lot of potential in many, many different areas, from insurance, intelligence communities to kind of like financial predictions and such. So
do you have a specific industry in mind as you think this would be best used for it?
I think that there are multiple industries. We haven't sort of looked at exactly. I think that obviously financial kind of like places is a good example. I think that intelligence community is a good example, and then like bunch of like anytime. I think that it's the problem that if you accurate enough and you can do better than any of the existing models, then the applications are. It's pretty obvious what the applications would be, right? Like from financials to intelligence to insurance. It's like. I mean, somebody was telling me pricing right now, insurance pricing for like fires in LA. There is a Polymarket for it, a Kalshi for it, which is much better prediction what insurance companies are doing.
Yeah.
right?
Yeah,
Because
that's the other question I wanted to ask you. So like, what do you think about using this decision system versus just using the outcome of, or like the probabilities on Kalshi or Polymarket?
that's a very good question. What we found is that the crowd prediction is actually pretty good. Like Kalshi Polymarket, people are, one person prediction is probably not good, but when you have 1,000 people,
And
10,000
potentially
people,
insiders.
so if we take insiders out,
Yeah,
so let's assume that there's no inside information. Obviously, if somebody has an inside information, there's nothing you can do, right? Like if I know certain event's going to happen, then I can't do much about it. But when you have the power of the crowd, like many people, and many people are betting money, then people become efficient, right? It's because when I bet money, I actually think I know what the outcome will be, or at least I can estimate it. And so the crowd prediction are actually very accurate, and it's one of the best predictors. Like if you look at the prediction of like elections or sports events or such, prediction markets are actually fairly accurate baseline, like very good baseline, right? Because otherwise, if it wasn't, people would kind of make money out of it. There would be arbitrage opportunities. I think that we can do better with AI. We can do better than prediction markets, than what people are doing. That's one hypothesis, because the access to information and the breadth of the information that you can process will be always bigger than any person can do.
Yeah.
But at the same time, imagine a system that can be just as good as the crowd, or even better, for any question, right?
Yeah.
Like,
and I'm assuming that you can also use the Polymarket information as an input into your system as well.
Of course.
At any moment
in
time. Yeah.
That's exactly right. But at the same time, imagine you can create sort of, it's almost like you're creating prediction market for any question, right? Right now, prediction markets are sort of centered around what people want to, and it's like the most popular categories are, I think it's like Bitcoin and sports.
Yeah. And maybe politics. Yeah.
Politics less so, but like Bitcoin, people want to know what's happening to the Bitcoin, and people want to know what's happening to the sports. Like those are the two things. And then, these are good. People want to, but these are very limited, in terms of trying to forecast where things might be, where the economy is going to go, and the prediction markets don't tell you the reasons for why, right? So you actually want to have a very strong reasoning system that can actually tell you why it's, 70% this team's going to win over this team. Why is this the case? Like who, and it's sort of, it's aggregation of the experts, it's aggregation of sports statistics, like what they've done and such, right? And so I think that ultimately AI is going to be, I like to think about this as like, and again, maybe it's a little bit of a kind of my just skewed view, but McKinsey. Why does McKinsey exist? Boston Consulting Group, these are big organizations, all of them should be replaced by AI, because AI is going to give you a much better information. Like McKinsey does these things where they say, well, company wants to invest in this thing. McKinsey goes, does the report, you have analysts doing research and everything, and they come to you and say like, hey, yeah, the probability of you succeeding is like 80%. I think this is the right decision. This is what you should do. And this, right? And this will all be replaced by AI.
Big statement. Wow.
I mean, all of this
I'm just saying,
like,
because those are huge businesses, right? So
those are huge businesses, but a lot of it is going to be replaced by, I think a lot of it, I mean, maybe you're going to have humans in the loop, kind of like, but there's no reason why. I mean, McKinsey and those guys, I mean, they have one of the caveats, which is the insurance caveat, which is, if I'm a CEO and I'm making these big investments, like a multi-billion investment, I'm hiring McKinsey. They go do the research to me and they tell me like, that's the right thing to do. And if I do it and I fail, right, I go to my stakeholders and say, hey, McKinsey also said this is a good thing to do, right? So that's the role that those companies play, right? It's like an insurance, but I don't think their predictions are going to be better. Like AI is going to be able to make much better predictions, because again, the amount of information it can process and everything is just going to be looking into the future.
Way more than a human,
They way more than like 10 analysts, or maybe you need one analyst working with AI.
Yeah.
I mean, maybe that's the scenario, because you still might need a human to kind of like, but
just coordinate things, but
exactly. But I think that and so this is like decision-making systems that can predict the future is going to be, and that's kind of like what I think. Again, I might be wrong. Maybe the whole thing's going to fall apart, because a lot of, I do have like a lot of opinions. Some of my best students are basically saying, I think it's a hard problem. It's not going to work. And it's great, And we'll see. I don't know, maybe it's a
Yeah.
hard problem, and maybe it's such a hard problem but to me, prediction markets was a confirmation that with the power of the crowd, it's the best prediction right now of any sort of model.
Yeah.
Right? It's very hard to beat the crowd, because if you could beat the crowd, you could make money, just off the culture and polymark. It's very hard to beat the crowd. It's not like you have a system that's like, well, I can just dominate, right? But it also points out that humans and the crowd itself is fairly efficient, and but I still think AI should be able to do better.
Yeah.
It's the wealth of information I can consume, and if I can build the right sort of systems to do it, we'll see. It's an interesting hypothesis to test. So
Yeah, for sure. So number one, I wanted to get your thoughts on all these Chinese distilled models. I think a lot of people are talking about this. Like, what are your thoughts on the impact of these models on the future of the LLM business in the US? Maybe like, the frontier models.
So I think that the models that are coming out of China are actually very good models. I don't know if they're distilling or not distilling. I mean, obviously Anthropic says they're distilling, but I have no idea. I do know. Do you know a company called Moonshot AI? They're releasing Kimi models.
Mm-hmm.
So the CEO of this company is Zhilin Yang. He's my former student at CMU.
Oh, cool.
So he is one of the smartest people I know. Like, he was a PhD student at CMU. He's like one of the best. And so China has strong talent, right? They now have the resources. So I think they'll be able to compete with the US. And
they're just making everything open source, which is crazy.
And then, which is, I think, to the community, like I can tell you, all of my students right now using Quen models, Kimi, DeepSeek, because these are the best models to do research with.
Yeah.
I mean,
and maybe GLM now.
And GLM is a little bit expensive, but it's a great model for distilling, for like doing research and such. So because these are open models, you can see the reasoning traces and everything. So I think that the strategy of open sourcing models is actually a very good strategy, because first of all, it gives academics, it also gives startups as a way to, iterate on these models, fine tune, see what works, see what doesn't work, right? And so now with GLM, the gap becomes fairly small. And so it gives opportunities for others to sort of, test and build upon, right? I'm actually very surprised that US doesn't have a good strategy for open sourcing the models. Llama was the last, Llama 3, Llama 4 didn't work so well, but Llama 3 was one of the last sort of good open source models that people were using and relying, and people are still relying on. But now I think it's a sad kind of state of affairs.
I have a hypothesis about this. My hypothesis is if these Chinese companies are actually distilling the like Anthropic and OpenAI models, well, they're not doing it in the US because of laws, and in China maybe they just don't care as much about following the US laws. So that's probably the main reason, is my guess.
I mean, it could be, but again, yes, if they are kind of like, but if they're open sourcing, then it kind of like also gives a whole bunch of startups and academics and such to actually have access to these models, run and continue developing the technology. Yeah.
So what do you think? So what do you think these like open source models, like the Chinese open source models, mean for the like US industry then? Like, what do you think? Like, how do you think the industry is going to have to evolve?
I don't know, because I think that at some point what's going to happen is that, I mean, there are a few startups that are kind of like very well funded. I think Reflection, that are supposed to kind of like produce strong open source models, but we'll have to see.
Yeah.
Llama was, again, I think Meta kind of like positioned itself differently now. I don't think they're going to be open sourcing the models. And so that's a sad state of affairs. I think that it's true, the laws in the US and what you can distill and such are stricter, but yeah, I don't know. I don't know how it's going to evolve. I mean, I think that we need more startups in the US, like who will, actually end the right. The problem is that you need a lot of capital to do it, right? And we know exactly what needs to be done. It requires infrastructure, capital, and GPUs to sort of, build an open source. But I don't know if US needs to do something, definitely US needs to do something about it.
Yeah.
Because it's kind of like said, like if you look at all the prominent startups and such, they all post-training, like even Cursor, right?
Yeah. They use Kimi.
They use Kimi to post-train the models, right? Because like, I mean, it's a good model, and then you just start post-training, and then a lot of startups doing the same thing, relying on Qwen, DeepSeek, Kimi, GLM to post-train because it's cheaper, way cheaper than frontier models. And if I can post-train, I can own the model. Like that's my model. Like nobody touches it. Like it's not like, people think that if it's a model coming from China, then somehow like the information leaks. No, it's contained. It's just the weights, right? And if I can post-train, it's my model.
Yeah.
And if
so
it has,
why?
yeah.
Oh, sorry. Go ahead.
And if base model is already good enough, kind of has base knowledge that I can post-train, and then it's great. I mean, I hear startups from speech and such, they're all relying on these open source models, post-training them and creating products out of them.
Yeah. I was going to ask you, why is it important for the US to have our own open source models? If the Chinese models are really good, then why do we need American open source?
Yeah, that's a good question. I think one sort of caveat is we don't know. I mean, for things like coding, that's fine. But for general knowledge, there is a little bit of bias that's being injected in any model, right? And so if your entire business relies on open source models produced by a different country, right? And so it might have some kind of like, you can ask it some questions about like Tiananmen Square, see what it does, right? Like there's certain kind of, nuances that some of these models, and I've talked to some people and they're like, yeah, we know that these models like math, coding, that's all fine. Like coding, there is no sort of political bias or like cultural bias, right? It's like, math is the same thing. It's like, here's the problem, this is the answer. Like either you got it or not. But more kind of, if you kind of, I don't know, use it for creative writing, or if you use it for like other things. So in the future, if you're going to be relying this as a ground truth source, like sometimes right now, I'm no longer going to, like, I do go to Google, but like sometimes you go to like Claude or Gemini and just ask it like, hey, tell me about this event. And it kind of like tells you, right? And I don't bother verifying. I just assume that it's truth. And so like these biases may come in, right? And so I don't know.
Yeah.
I don't know.
Yeah. Yeah. So another question was, so it seems like there's a ton of these like RL environment businesses or these data labeling businesses that are sprouting up all over the place. Do you think that is a sticky business? Like it will be around a few years from now?
No, I don't think it's a sticky business. I mean, people who are building RL environments and building a good environment is obviously important, but what I've seen right now, especially in the environment space, now that the coding's become so good, creating these environments just becomes cheaper. And I don't know. I suspect there's still going to be like a couple of players, big players, who will provide the environments, the data, because you need the data. And people who work very closely with the frontier labs and such, they might survive, but I don't see it as a sustainable business long term.
Yeah, especially because you were saying because of synthetic data, right?
Synthetic data. And then the other thing is that like I think like some of these businesses are now trying to shift towards robotics, and I suspect a lot of them will, right?
Like OpenAI and Anthropic are shifting to robotics, or
no, some of the data collection.
Oh, I see.
Right, like people who kind of like develop data, like collecting data environments, they're trying to kind of like see, okay, like can we go into the physical world and start collecting data in the physical world for robotics applications? So these data kind of like collection companies will adapt. But obviously, there's always going to be the need for, frontier labs when they deploy the models, they kind of like find some edge cases. They might go to these data kind of like, or these companies say like, create me an environment, create me the data so it can kind of like fix those edge cases. But I don't know.
Yeah.
I don't know. I mean, data is definitely going to be important no matter what for physical AI but I still think there's going to be maybe a few players.
Yeah. Okay.
But not like, there's so many people building RL environments. I think it was 2 years ago, it was like people like, okay, we need those because we can train our models. Now they're just becoming cheaper, and it's probably.
And now like, I don't know if you saw, like, do you know the company Handshake? So Handshake was this platform where like a lot of undergrads would use it to get jobs. And now they've basically pivoted to selling data to the lab. So it's like this weird dystopian thing where it's, oh, you were trying to get undergrads jobs, but now you're basically telling the undergrads to label data for the labs to basically take the jobs that the undergrads were trying to get in the first place.
Fair enough. Yes. I think that's kind of like, yeah. I mean, data is still like high quality, good data is still going to be valuable. And humans collecting the data, high quality data is still going to be valuable, and so that's why they're probably selling it, because it's valuable. But I agree with you. It's kind of like it's weird, kind of.
Yeah. So my next question was on SaaS. So it seems like a lot of people are very scared that basically this is like the end of SaaS because it's so easy to copy software now. What are your thoughts on that?
That's a good question. I don't know.
Okay.
I don't know. I think that the SaaS companies, that the software companies will need to adapt. A lot of it is based on how much moat they have, the client relationships and the legacy software they have. But I do think now with these agentic systems, the coding systems, like, SaaS is going to take a hit.
Yeah.
Like it depends how it's going to evolve. I mean, we've seen, so for example, Salesforce been down for like a lot in the last 2 years, right? ServiceNow, same thing. Like these all SaaS kind of like companies, even Snowflake and, those kind of. So I think that they'll have to innovate. I think that software is going to be cheap.
Yeah.
Do
you agree with people when they say that the cost of intelligence is approaching zero now? Is going to zero?
I don't know if it's going to go completely to zero, but what's going to happen is that if you have models like 5.6 or Mythos, right, super expensive, it now basically comes down to intelligence per token, like cost per token, like how intelligent your model is and how efficient it is, and how cheap it is.
Compared to a human, essentially.
Compared to any other models.
Okay.
Like, like I was talking to, who was I talking, like somebody at LinkedIn, and then they're like, well, early on they were trying to use like 8B or 9B models because these are cheaper models, and for what they do, that's enough. So there's this notion of intelligent. You obviously want to have intelligent models, but then the cost is the other kind of like, I want intelligence, but I want to have it at a very low cost. And so obviously like these inference, like all these people doing inference chips and whatnot, they're all trying to basically say, I want to be able to give you intelligent tokens, but for cheaper. So I don't know if the cost is going to go down to completely be close to zero. And this is where open source models are kind of like coming on, right? Because they're like, hey, they're intelligent, but like 10th of the cost. I mean, as a business, of course, I'm going to be using that. Like maybe it's not at the same level as Mythos, but it's good enough for what I do.
90% of the way there for 10% of the cost, something like that.
Yeah, exactly. And then that's a good business argument for me to use it, right? Like, I mean, why would I use? So I don't think it's going to go to zero. I think but it will be cheaper and cheaper because there is always ways of distilling these models into smaller models.
Why do the frontier models keep getting more expensive? Is it just because they're using up more compute?
No, because I think there is a demand.
Okay, so it's just they want to increase the price.
They want to increase the price. There's a demand. And then, there's been some wars before, right? Like, I mean, like I've seen these examples where OpenAI would say like, here's our price. And then like 2 months later, they would like cut the price by like 5. Okay, why'd you do that? I mean, they're doing it because it's competition, like because there are cheaper models that might be just as good, maybe a little bit worse, but like way cheaper. So it's all about, and this is where the efficiency comes into play. Intelligence is one thing, efficiency is another thing. So like it's brutal because, if I can do my job at 90%, but at a 10th of the cost, maybe I'm okay, kind of,
maybe it makes sense.
Yeah. Economically, and it's like, economically, I think it's all going to come down to economics, right? Like, because I can't, whatever is cheaper, I'm going to use.
So you think that all the LLMs are basically commodities?
I think they're going to be commodities. Yes.
Wow. Yeah, I mean, it's interesting because like early on when the LLMs first came out, that's what everyone was saying. But then, then all the labs just kept competing with each other, kept like outdoing each other. But yeah, it seems like everyone's basically converging back on that point, which is they're basically going to converge on the same thing.
Yeah. I think that's like, some models are going to be a little bit better, and it's all now is going to come down to the product. Like, Codex and Code Cloud is a fantastic product, like, because you can integrate itself with your code base and everything. And then like once you kind of like, when it becomes sticky, kind of like use it, right? Even if somebody's a little bit better, it's all going to come down to like products, like what product you have and how easy it is to use and how cheap it is.
Yeah.
Right. That's
what are you really excited about that's happening in the industry, maybe research wise or otherwise, that you think is going to create like that next step function change in what's going on?
It's a good question. I don't know. I mean, there is a lot of work on self-improving systems, self-improving agents, self-improving, which seems to be promising. So these systems, again, this is notion of you have existing models, it generates some data, you filter it, you use this data for training, or you use like these sort of what we call parallel systems where you do rollouts, you do multiple rollouts, you figure out which one solved the problem, which ones didn't, and the ones that solve the problem, uses the data for kind of improving the system. So, like AI that kind of like self-improves and getting a little bit better is one direction that people are looking at, which is an interesting one. I think decision-making, forecasting is going to be another one. And I think the third one is robotics. It's sort of like this notion that this is one big area that we're missing right now. And that's the area where there's probably going to be a lot more investment, but it's also the area that's going to take the longest to actually produce something meaningful.
And for robotics, you're specifically talking humanoids?
It doesn't have to be humanoids, but it's kind of like one of those things is that somebody was telling me, which robots kind of like have shown to be useful, like actually kind of, people use in the real world. And there's only one example, which is Roomba, right? Just cleans your house. There's no other example right now where a robot is useful, where I would pay like whatever, 5,000 for it to like do stuff for me.
Yeah, for consumers, I guess, right?
For consumers. But even for enterprises, I mean, yes, there is like manufacturing and stuff like that, but even there hasn't been, I mean, if you look at Amazon, but all the robots of like kind of like moving things around, these all like predefined. So these are not really robotics. It's more like, a system that like moves things around.
Yeah.
It's all like very specific, or like assembly robots, like they're all very specific, right? It's not, but there aren't any examples where you would basically either in enterprise, maybe, I don't know, maybe there's some enterprise, but consumers in enterprise, like it's not like, hey, here's Tesla Optimus that goes and like assembles the cars and like replace like 100 humans.
Yeah.
It's just not there, right? So, and it's going to take, I mean, the best case we have right now is self-driving cars as kind of like the actual robot that sort of does something meaningful. Others have not. We see these examples, people like cooking, like robots cooking or like doing stuff, they're walking around but it's all at this point, it's still yet to come, and so I think that's the area there's going to be a lot of research and development and investments as well.
Why is that not progressing as fast as LLMs?
I think one of the things in robotics, we've seen examples of like robots doing like backflips, dancing, moving around, like locomotion, going up and down the stairs. It's all great. That's the progress. One of the biggest bottlenecks right now in robotics is manipulation, like the ability to actually do useful things,
with your hands specifically.
With your hands, or doing any sort of like, can the robot clean up my kitchen? Can the robot like load my dishwasher, wash it for me, unload it for me? Can my robot like, if it's a factory, can it go and like do some kind of wiring, right? Or do like multiple tasks and do it reliably, not just sort of like, people show that it's like sorting, can kind of like sort and things, but it's like very, very sort
like
of
toys.
Like, and very carefully structured, like little things of the whole thing will kind of, there was this funny, and so like manipulation, like the ability of actually do meaningful tasks is still not there. Manipulation is one of the big problems that like, it's not
but
there.
What about that is difficult? Because it seems like, okay, so for example, for self-driving cars, the big unlock was just throw tons more data at it and it'll figure it out. Why can't we just do that with manipulation?
Yeah, so for this one, it's difficult because like we don't have good hardware, universal hardware. Like Tesla develops its own, Unitree develops its own. Like everybody's developing its own. That's number one. And number two, building 1 million robots that will do data collection is very expensive. And so you need sort of like, and so this data collection and manipulation and everything is still like very early right now.
I see.
And so like, this is what the data collection kind of like companies are trying to pivot right now to sort of say, well, we can take humans in the factories, put,
goggles on them, record.
And then and then they collect the data for robots, right? I mean, maybe that's the way to do it, but nobody has figured out like what, how to use that data efficiently, right?
Yeah.
And for LLMs, like the data is on the web, like that's unlocked, right? There's no like internet scale data for robotics. It's just not there.
Yeah. Maybe that's why Apple is trying to put cameras in the AirPods now.
Could be. I don't know. Yeah.
But yeah. So my last question was, if you were in college right now, what would you study?
Good question. My view are going to be very biased. I think studying STEM related areas, I still think that's the right thing to do. I think that studying computer science, statistics, AI, machine learning, that's what I would do. Obviously, there is like engineering, computer engineering, and engineering efforts. Like anything sort of like in STEM, I think, is going to be relevant.
So you don't agree that we should just stop studying computer science? Because you've probably seen the graphs on Twitter where it shows like the number of Stanford CS majors has gone down by like 40% in the last 2 years or something.
My kid is going to be kind of like at some point, a few years from now, applying. I do hope that the trend continues because it's going to be easy to get into computer science. Like in the last 3 years since AI took over, like CS, like, I mean, you can see at CMU, our PhD applications over the last 5 years just skyrocketed. We have 1,200 applicants applying for PhDs. We accepting like 50. And these are like strong people. These are not like, kind of like B and C type of students who are applying. Like these are
best of the best. Yeah.
Best of the best, right? And so, for undergrads, I don't know. I actually think that in the future, maintaining these systems, improving these systems and everything is just going to require more and more computer scientists. And look at the job applications. Like there's so many openings right now. Like if the whole thing was automated, like even Anthropic is hiring a bunch of software engineers or like ML research engineers, right? It's I don't know. There's an argument for like, if things completely shift certain way where, these agentic systems going to be writing the code and everything. And then, like psychology and social sciences and such, where like a little bit of a human interaction is needed, might go up. But I don't know. I think that technical people will always be in demand.
Yeah, I agree. But then there's people who say, don't study anything that's verifiable.
Verifiable like math?
Verifiable, like you were saying, where we can easily spin up RL to train on it to give it the answer.
My view is like, I mean, maybe like it's going to be a little bit controversial view, right? Which is math. If I take math is a fantastic subject to study in like high school and college, but it's probably not kind of like useful, like if you're studying like all these abstract kind of, abstract algebra and like all of these sort of like crazy, maybe it's not really applicable in the real world, right? So only few people kind of like very smart people kind of, stay in this area. But studying math gives you the analytical thinking. So when you study computer science, when you study like data structures and everything, it just gives you a very analytical way of thinking. And to me, that was like extremely useful for me to kind of like go and do research in that area.
Yeah. So like the logical reasoning ability.
Exactly. Yeah. It's the reasoning. It's like math. It's just like, I wouldn't go and kind of like go and do like pure math as my career, right? Because I don't find it's appealing. I mean, some people do, I don't, but I did major in computer science and math. And the reason why I did math is because I thought that this gives me strong analytical abilities to think, and whatever the future is going to be, you always will have to adapt. People who are able to adapt will sort of be on top of things, right? And so,
Yeah.
So
do you think that the skill sets that will matter in 5 years are the same skill sets that mattered 5 years ago?
I think it will change. I think the change will come with the use of AI.
Yeah.
So, and I can see it. I have a kid who is now in high school, and then they just basically using VS Code, Claude, and building websites, building startups and stuff like that, right? Because you can do it right now. And so people who can have these strong analytical skills, plus able to, use these AI tools and shift and kind of like make the use of both, are going to be at the top.
Yeah. Right. So like hustle plus just that, you can just move fast, essentially.
Yeah. You can move fast. Yeah. I mean, it completely changes and people who don't use AI tools are going to be left, and I've seen this, like some of the smartest people. I mean, it will be interesting to see, especially people like in the 30s right now, who kind of like 30s and the 40s who like built, have in now like this rapid shift right now. You have to adapt. So you have to know how to use these tools and make kind of like, be more productive. I think that's, I'm seeing it with my PhD students. They're like, my workflow has completely changed in the last year.
Yeah.
Now we're interacting with AI tools, and I can sort of like say, let's do this, and kind of like before it would take me 3 days to code something up. Now it takes me an hour. And so if it takes me an hour, I can actually progress on my thing. And so people who can take advantage of this, they're moving way faster.
Yeah. And then I've seen a lot of people that are like losing their identities because they're like, I just spent my entire career learning, like being a good coder. And now I can just do what I learned in 20 years in like 20 minutes, basically. So yeah, there's also that side of it. Yeah.
There is. Yes. That's kind of like, yeah, there's, and it also happens in academia because there's a lot of people who worked on like dialogue systems and everything, and it's like completely changed.
Yeah.
But change is inevitable, right? Like, so kind of like you have to, it's like you have to adapt. Like but it's I think it's exciting development. Like, I mean, it's definitely changed kind of, and it empowers, like, I mean, I do coding, but now I can be so much more productive, right? Like I can actually go and, I'm doing this thing with my students, and it's like some weird, bizarre error on some of the packages. It would take me days to figure out, because I would go to Google and say, I have this error, what do I do? And it's like, look at this. Now I can just ask Claude, like, this is an error, like, just figure this out for me, how to install these things. Like, I don't even need to think about, like, that's not what I want to think about. And just like, sure, like this and this, and gets to the right thing that I don't even have to think about, right? So
yeah. Awesome. Well, I mean, those are all the questions that I had. Thank you for staying over.
Awesome, Vasil. Well, thanks for having me.